Hey guys, and welcome back to Miss Chemistry. And I did promise I was gonna post a Proton NMR video today, so here I am now. So let's look at solvents. Now you have to know this. I'm so sorry, but you have to know this. So samples are dissolved in solvents without any hydrogen atoms, such as CCl4 and CdCl3. You have to remember these, so you have to use like 1-mark questions, because they might ask you in a question, identify a solvent in which it can be dissolved before obtaining its proton NMR spec, and before obtaining its proton NMR spectrum means without any hydrogen atoms, so it's either CCl4 or CdCl3. Oh my gosh. Okay, so this means that in the proton NMR, the solvent will not give any peaks. So not the molecule, the solvent won't give any peaks. And TMS, tetramethylsilane, is added to the sample to calibrate the spectrum. Now you need to know just about TMS. You don't need to know really about how it calibrates the spec, but you just need to know about TMS, tetramethylsilane, and you need to know why TMS is used. So it's because its signal is away from all of the others. It only gives one signal. It is non-toxic, it is inert, and has a low boiling point, so it can be removed from the sample easily. Now, I think you should remember at least 3, but they might put 2 in the question, so they might be asked like, oh, give 2 other reasons why TMS is used as a standard in recording the NMR spectra, instead of it saying that it's non-toxic or is inert. So I would say remember 4. So I would remember it only gives one signal, it is non-toxic, it is inert, meaning it's unreactive, and that it has a low boiling point, so it can be removed from the sample easily. And you have to know what it looks like as a structural formula. So that is what tetramethylsilane looks like. Now the keywords you need to know for NMR and proton NMR, well, the whole of NMR, but mainly proton NMR, is relative intensity / integration values. So relative intensity and integration values are the same, like they mean the same thing, but they might put any of these words in the exam question, and these mean the number of equivalent hydrogen atoms, which means the number of hydrogens on each carbon. So basically the number of hydrogens on each carbon, but in a more professional saying, the number of equivalent hydrogen atoms. Then now you need to know about the signals. So signals is basically another word for peaks. They might ask you for the signals instead of asking for the peaks, so be careful of that. So signals is basically the number of peaks in the carbon NMR or the proton NMR. Well, it's basically what the exam question asks you to do. And the splitting pattern. So they're the type of pattern shown in the proton NMR graphs, which is the singlet, the doublet, the triplet, and the quartet. Now don't worry, it can be difficult, but it is simple when I break it down. So that's the splitting patterns, okay? Now you guys need to learn how to identify the proton NMR. So here I am. So proton NMRs only focus on the hydrogens, guys. So for example, we have this molecule on the top left. This is ethanol, and what I would do is the letter thing again. So I'll look at the hydrogen, so I can see that there's that hydrogen A, and it's bonded to a carbon, which is the same as the other 2 hydrogens bonded to that carbon, so they're both hydrogen A. And then the other hydrogen is on the O. Not on to that yet. The other hydrogen is on the other carbon, and it'll be different hydrogen because it's not the same, so that'll be B and B because they're both bonded to the same carbon. And then this hydrogen is different because it's bonded to an oxygen, meaning that molecule, I didn't write it down, I'm sorry, but I'll write it down now, meaning this has 3 peaks / 3 equivalent hydrogen atoms / 3 hydrogen environments, different hydrogen environments. Okay, we have this molecule here. So of course I will look at the hydrogens. So I will see the hydrogen. So I sometimes I go left to right if it's easier. You can go from left to right, right to left, whatever. So this hydrogen on the carbon here would be A, and the same hydrogens on this carbon would be A as well. And then these hydrogens, and then you can see the methyl group on the bottom, on the second carbon, the methyl group. These hydrogens are going to be the same because there's also a CH3 here and a CH3 here, and they have the same, like, they're not bonded to the same carbon, but they're bonded. Oh my gosh, I can't erase it. I'm so sorry. As I was saying, they're not bonded to the same carbon, but they're both bonded. But these two carbons are both bonded to this carbon, so they are the same. Okay, and then the next one, this hydrogen on that carbon really circled is gonna be B, is gonna be different. Then these hydrogens are gonna be different as well, and then these hydrogens are gonna be different as well. Remember the symmetry, guys. Okay, let me do my symmetry line if it's more easier. Like my symmetry line, there's my symmetry line, and you can see which hydrogens are different, which hydrogens are the same, you know, so forth, so forth. So therefore, this would have 4 peaks, which means 4 sets of equivalent hydrogen atoms. Now, if I'm gonna see, you remember the integration values, the relative intensity, basically. So as I said, the integration values are the number of hydrogens on each carbon. So for example, on the carbon A's, you can see the carbon A's right here. I just basically count how many hydrogens are named A on the carbon A. Basically just count the number of hydrogens that are written A. So there are 6 of them. Then on hydrogen B, there's 1 of them. And then hydrogen C, there's 2 of them. And hydrogen D, there's 3 of them. So that's how the integration ratios work, and that's how the integration values work. Now let's look at this molecule. So I'll go from left to right. So the CH3 on the left is those hydrogens are definitely different. That's an A. The hydrogens on the adjacent carbon is definitely different. It's B because it's bonded to a C-double-bond-O. C-double-bond-O has no hydrogens. Okay, now we look at the right hand side. All those hydrogens are the same. They're bonded to the same carbon. Therefore, there are 3 peaks. And if I was going to write the integration ratio, which was the integration value / relative intensity, there's 3 hydrogens on A, so and 2 hydrogens on B, and 9 hydrogens on the C. Now, oh my gosh, wait. Guys, I am sorry. It didn't pop. The drawing did not pop out the way I wanted it to. So, yeah. Okay, so here, this is okay, you know what? I'm gonna redraw it. Okay, so I redrew at the bottom. Don't mind the hydrogen at the top. I was gonna do that later, but then I just realized. So, if I was gonna do the hydrogen NMR of this, like, benzene ring, obviously these 2 hydrogens will be different because they're bonded to an oxygen, so they'll be A's. And then I would draw out the hydrogens that come out just to see them. Okay, so these, and then all of these hydrogens are the same, so they're all B hydrogens because they're all bonded to an OH, basically. So therefore, oh my gosh, therefore there are 2 peaks. And yeah, okay, and then this last one we're going to do. So, as I can see, but the hydrogens, so I'm going to start from right to left. So those 2 hydrogens on the right carbon, they are definitely the same. And this top hydrogen, which is C, is different. And then the hydrogens on the B is definitely different because there's 3 hydrogens bonded to another carbon, bonded to a double bond carbon. And then the top hydrogen is different because it's just bonded to the double bond carbon. It is not the same as the carbons on the right because the C hydrogen is also bonded to a carbon which has a methyl group. So therefore there are 3 peaks. Okay, so what I'm showing to you right now is basically what's on the back of your periodic table, which is next to the carbon 13 NMR. So these values here, the ppm here, they basically say they say what the hydrogens are next to, like what the carbons are next to, like what's on the adjacent carbon, basically. What's on the adjacent carbon. Sorry, the handwriting is very bad. So for example, there's a C double bond O here and there's a CH2 here. Now the CH2 is gonna go here, and I'm gonna show you the splitting patterns later. This is a quartet because there's 4 peaks, but I'm gonna show you that later. So this CH2 is here, and then this is about, and then when you look at the ppm at the bottom here, you're gonna see what the measurements are. So I can't rub that out, I'm so sorry, but behind that Q it's gonna be 2.1 to 2.6 because there's a C double bond O next to this, so it'll be 2.1 to 2.6. So that basically shows you what's on the adjacent carbon. Okay, so now I'm going to introduce the splitting patterns. So this is what they look like. So here's our singlet, our doublet, triplet, and a quartet. And by its names, it's kind of obvious. So singlet, single, you're single, 1 peak only. A doublet, double, there's 2 peaks. Triplet, triple, 3 peaks. Quartet, quarter, 4 peaks, okay? And then you have to guys know about the N plus the rule. So N plus rule is basically the number of hydrogens on the adjacent carbon, but it's like -1. Okay, that was confusing, but let me explain. So, okay, let's look at our singlet. Our singlet here, okay? So let's say that's our singlet. Its peak is 1, right? So if we do 1 minus 1, it will equal 0. Therefore, on a singlet, there are no hydrogens next to the singlet, because there's 0 hydrogens next to the singlet. Okay, let's look at the doublet. 2 minus 1. Okay, guys, I'm back from the toilet. Okay, so what was I saying? Okay, so the doublet has 2 peaks, so 2 minus 1, which means it's going to be 1 hydrogen on the adjacent carbon. When I say adjacent carbon, I mean the carbon next to the carbon. That makes sense. Don't worry, we're going to put this all together in a question and I'll show you guys. Okay, if it's a triplet, that means there'll be 2 hydrogens next to it, because 3 minus 1. Sorry, I'm catching my breath. And then if there's 4 peaks, that means there's going to be 3 hydrogens next to it. 3 hydrogens next to it, because 4 minus 1 is 3. Okay guys, so now we're going to do an exam question and I will show you an example. Okay guys, so let's get into our question. You can pause the video if you want to do these questions, but I'm just going to go through them. Okay, so we have C3H7ClO. Okay, also guys, I got a new pen, so better handwriting. Okay, so they gave us the chemical shift values and integration values. As I said, integration values are the number of hydrogens on each carbon, and since they are in decimals here, we can make them into whole numbers. So if I times it by 10, it would be 6, 6, 9, and then make it the simplest whole number ratio. So now I divide it by 3, so I would get 2, 2, 3. Yeah. Okay, so I figured that out. Now, what I'm going to do next is I'm going to draw a table. If you draw a table, you get your straight 5 marks, 6 marks, whatever. If you draw a table, you get your 5 marks, all your 5 marks, trust me. Okay, so I'm going to do the chemical shift here. So chemical shift, integration values. So the splitting pattern, guys. Don't forget the splitting pattern. So splitting in short, and then I'm going to put the fragment structure. So yes, we need to do the fragment structure so we get our 5 marks. You want that, don't you? You need to do the table. Okay, so if I just do a short table, I can make up to this line. Okay, so first chemical shift is 3.95. Integration value is 2. The splitting pattern, okay, so 3.95 would be around here. So it is 3 peaks. So it's a triplet. So I'm going to put triplet here. Okay, we're doing the fragment structure after we fill in the chemical shift, the integration values, and the splitting patterns. Okay, let's look at 3.65. Integration value is 2 also, and the splitting pattern is also a triplet because there are 3 peaks. And then the last one, 3.35. Integration values is 3, And the splitting pattern is, let's see. So it's a singlet because there's one peak, guys. There's only one. So it's a singlet, which means no hydrogens are next to it, remember? Okay, so guys, remember the n+1 rule. If it's a triplet, there will be 2 hydrogens next to that carbon. Oh, there'll be 2 hydrogens on the adjacent carbon, which is next to the carbon. And then if it's a singlet, there's no hydrogens on the adjacent carbon. Okay, so let's figure out the fragment structure. Now, let's look at our periodic table, guys. The back of the periodic table, go look at that. Okay, so 3.95 is, okay, it's going to be here. It's within the range of 3.1 to 4.2, that's where 3.95 is. So therefore, it's going to be a chlorine on that carbon. So if I was going to draw it, I'm going to color code it. Okay, yeah. So if I have a C with my 2 hydrogens, usually I do it structural, but I'm going to do it space so it's more easier for you guys to see. Actually, let me redo it. Sorry. Okay, so let's say I have my 2 hydrogens on the integration value there. And since it's a triplet, there's 2 hydrogens next to it, so I can write it in any order I want. There's 2 hydrogens next to it, because it's a triplet, remember? That means there would be a chlorine. The fragment structure, there will be a chlorine there. Oh my gosh, oops. That means there will be a chlorine over here on that carbon. I should put in any carbon, to be honest. But, yeah, I could put the chlorine there, or I could put the chlorine, oops. Chlorine there. To be honest, I'll put the chlorine here because it is on the adjacent carbon, so I'll put the chlorine there. Okay, next we have 3.65. So guys, 3.65 is actually here. So that's the 3.65 is within the range of 3.1 to 3.95, and that means there's an oxygen next to that carbon. So if I was going to draw it out, also you can put an R group just there. You don't need to, but it's better if you put an R group. So if I was going to do it, then I would draw the carbon with the integration values. So there's 2 hydrogens. It's a triplet, so the adjacent carbon would have 2 hydrogens because the n+1 rule. And then there would be an O because it's part fragment structure. Put an R there, like the R group. So there'll be an O because that's the fragment structure. Remember the range for 3.65, and then the last part 3.35. So guys, I can see that 3.35 is within the range of also 3.1 to 3.9. So therefore, that the carbon with the integration values is next to an oxygen, and it's a singlet because there's 0 hydrogens on the adjacent carbon. Remember. So therefore, if I do my integration values here, and then my spin pattern, where there's where there's 0, sorry, it's a singlet. There's 0 hydrogens next to it. Therefore, my fragment structure would be next to the O, oxygen. And there's R group and there's R group. Okay, so now let's look at it like a puzzle. Okay, it's like a game. So let's look at a puzzle. Okay, so if there's a chlorine, so if there's this, that means that's going to be at the end of the chain. And also we have, oh wait, guys, sorry, I meant since it's oh my gosh, integration value is 3 hydrogens. There'll be 3 hydrogens on that carbon. I'm very sorry. Let's continue. Okay, and then this means this will also be at the end of the chain. So they're both at the end of the chain. Then we can interpret that it will be this. And that is your answer. Easily done. That's an easy 5 marks, guys. That is your answer. Okay, it's like a puzzle. And if you look at the marks game, we got this mark for the integration ratio, and we got the fragmentation right, we got the splitting pattern right, and yeah, we got all our 5 marks. Okay, next question, guys. So the proton NMR spectrum of a compound with the molecular formula C9H18O2 is shown. Deduce the structure of the compound. Okay. So if you can't see that, it's C9H18O2, and then this is our graph over here. If you can see it clearly, I want you guys to try this question out, and I'm gonna go through it now, so you can pause the video. Okay, so first let's look at the splitting pattern. Let's see what splitting patterns they are. So number 2, this one is a quartet, so I put it as Q. This one is a singlet because there's 1 peak, so therefore /1 signal. When peak and signal are the same thing. So number 2, this is a singlet because it's 1 peak. Number 3, this 3 is definitely a triplet, so I put as T. This long 1 line is a singlet because it's 1 peak. This 3 is a triplet. So, and then this 2 is a quartet. There's like a little, sorry. There's like a little spike there. So it's a quartet. I was about to say triplet, it was a quartet. So it's very hard to see it sometimes. Okay, so now I'm going to do my table like in the last one. So chemical shift. Integration values. Splitting pattern. And then our fragment structure. So this is kind of a hard question. So if you guys went through it, did it, then well done. Okay, so let's start with this one. Okay. So it goes up in 0.5. So this will be 0. Wait, no, it goes up 0.2. So it goes up in 0.2. So this will be 0.2, 0.4, 0.6, 0.8, and then this 1. Okay, so this quartet is about, so this is 4.2. It's like It's within that range. So if you look at the periodic table, like in all honesty, basically it's more than 4. So it's C9H18O2. So I'm gonna say, okay, let's see. So it definitely can't be an alkene. Therefore, it has to be within this range. And it can't be this also. So it's definitely this one. Also, they might give you like a range. So for example, what I got is like up to 4.2-ish. And even though 4.2 is not within this range, it still counts because they might give a little over the range. So you have to be careful. So therefore it'll be this an S star. So I'm gonna put for the chemical shift value like the same as the periodic table one, 3.7 to 4.1. And integration value. So it says integration values here, so it says in the question already, which is nice of them. Okay, and it's already the simplest whole number ratio. So there's integration values 2, and the spinning pattern is a quartet. If it's a quartet, n-1 rule, that means, since there's 4 peaks, n-1 rule, that means there's 3 hydrogens on the adjacent carbon. So if I was writing the carbon with the integration values, and then spacing pattern, so it's next to 3 hydrogens. So actually, let me quickly move this on the other side. Oopsies, hold on. Okay, so this is what it would look like. This is my carbon with the integration values, 2 hydrogens on it. Then on the spacing pattern, there's 3 hydrogens on the adjacent carbon. Adjacent carbon means the carbon next to it with the integration values. So this is that one, and that means it's going to be like towards the end. So that's a big clue that it's going to be like at the end. And then here's our fragment structure of our chemical shift there. So let's do the next one. Okay, so the next one is a singlet, and it's like, so this is 2.2-ish. It's on the periodic table. It would be around, let me see. It'll be around the 2.1 to 2.6 range on your periodic table. I'm not going to show it again because it takes too long to load, so I'm very sorry, but you have your own periodic table, so go and Google. So 2.1 to 2.6, the integration value is, what is it? It is 2, and the spacing pattern is a singlet. Sorry, a singlet, hooray. Okay, and if I was drawing my fragment structure, guys, also you can draw it in structural formula, but I'm going to draw in display so you guys can see it more clearly. Oh wait, since it's a singlet, that means it's not next to any hydrogens. 0. So therefore, I'll put like a R there, and then it'll be next to C double and O. Right there. Then there's an R. Okay, next one. Oops. See, I like making these tables, you know. Like, this is like a very, like, you know, neat, you know, type, you know what I'm saying? Okay, next one, this is a very long molecule, which is what makes it quite hard. Okay, so next we have, so here the range is about like, how do I say, so if it's 1, it's like 1.2-ish, so I'm gonna say it's like, what should I, it's like next to like a CH3-ish, so I'm gonna say it's in the range 0.7 to 1.2. And the integration value is 3. 3. And it's a triplet, meaning n-1 rule. There's 2 hydrogens on the adjacent carbon. So if I was going to draw out. Okay, this looks like an ending as well. Just to note that down. Okay, so it's either this is 0.7 to 1.2. So since it's already a CH3 and it's next to CH2, therefore it's probably not the 0.7 to 1.2 range. It's probably the 1.2 to 1.4 range. Okay, next. And I'm doing this really slow, but this is just for like the people, you know. Okay, so this one makes it really hard. There's a 6 as the integration value. Okay, and this is like, you know, at this point you can just start estimating the ranges, like like 0, like this is past 0.8. So I'm gonna say, okay, this gives a big clue actually. I'm gonna say like 0.7 to 1.2 range. And these are 6, and it's a singlet, meaning that there's no hydrogens on the adjacent carbon. Okay, so since there's 6 hydrogens on this carbon, that means it's going to have methyl groups, guys. So it can have a CH3 there, and a CH3 there. 6 hydrogens on that carbon, and then next to it, since it's a singlet, there's like no hydrogens on the adjacent carbon. So I don't really have that much information right now. But what we do know is that it's definitely next to some oxygen, because there's 2 oxygens, remember? So it's definitely next to some oxygen. So I'm gonna leave it. We're gonna put we can put an R group there. This is next to like an oxygen. Okay, guys, don't forget that. But definitely. Okay, and you guys can do the rest. I'm just gonna load the rest of the table. Should be pretty straightforward. Okay guys, so this is the rest of the table finished. I just did in structural formula so it'll be more faster. And what I inferred for this R group here, since there's no adjacent hydrogens since there's no hydrogens on the adjacent carbon, that it must be after this part. So I'm gonna put, and there's 2 oxygens, so the C double and O and O. It's R group there. Okay, so now we can figure out what the molecule looks like. So as you can see, we have our end piece here. So I'm gonna put our end piece, our CH3, and then put a CHH there. Then got a C double bond O with an S double bond right there. And then this. And then you can see here, this part is next to the S double bond. So I'm going to put a CH2 there. So CH2. And, oh my gosh guys, wait, I think I made a mistake. Ah! Okay. I'm sorry guys, it is literally 1 AM right now. Not healthy, don't do this. But the reason why there's okay guys, I'm just gonna freeze and do a little pause because whatever nonsense I said in the next few seconds made no sense at all. But the reason why the molecule's gonna look a bit different, and that the C with the 2 methyls is gonna be next to a CH2 even though it's a singlet, it is because of the other singlet, which is the carbon with the 2 hydrogens. Remember the second one, the other singlet, it is going to be next to a carbon with no hydrogens, adjacent carbon with no hydrogens. So it would definitely be next to the ester bond, and it'll be next to the carbon with the 2 methyl groups, because that carbon with the 2 methyl groups has just the methyl groups with another carbon on it. I don't know guys if I'm making any sense right now, but the central carbon with the 2 methyl groups attached to it with that middle carbon has no hydrogens on it, only like the methyl groups. Group's gonna go here because it has to fit the puzzle. So therefore, if there's a CH3 there, then these 2 are left. So put a CH2, sorry, and then a CH3 there, and that is your molecule, guys. That is it. I'm sorry for the confusion. You know, I try to help you guys as much as I can. I put my all and energy into my videos, and I get a bit tired sometimes, you know. So like, excuse me.